It is either liquid or solid, right? Alpha phase or liquid phase. But somehow, if you have a TB temperature assuming to be 1250, the composition is about 35% of the nickel, which is here, and then the intersection would be this point. You know the phase at present is liquid plus alpha. But then how many percent of liquid? How many percent of the alpha? So what you can do is that you draw the tie lines. You draw the tie line until it touch the boundary regions for each of the phases. Right? You cannot exceed this line. Because this one is you already have 100% of the liquid. This one you have 100% of the solid. So but then for your case you have two phases. So once you know once you draw the tie lines, the ties at points, then you draw the vertical line. So for this case, you can identify the compositions of liquid and also alpha. Okay, so this one is the compositions lah. Compositions of the liquid Cl consists of 30% of the nickel. The remaining is about 60% of the copper. But for solid, it consists about 43% of the nickel, this one, and remaining, which is about 57% of the copper. So that is actually how you write the compositions. And same thing as well. Once you know the temperature and compositions, you will calculate the amount of fractions. How many percent of the liquid that forms, how many percent of the solid that forms with respect to these compositions. Okay, for this case, right, after you draw the timeline, you need to label those regions. C naught normally is given to you. So you label the region for both sides, for example, like R and S. In case you wanted to calculate the amount of fractions for the solid, you calculate this region, which is opposite to this. So R divided by total regions of this, R plus S. The combinations of liquid and solid, it will give you 100% of it. So that's why when you calculate the solid regions, 27% of it, just minus with hundreds, you get the remaining liquid of 73% of the liquids. So at this point, you still get 70% of the liquids. Okay. So the thing is that, for example, like I reduce the temperatures a bit, close to 1230. This is to 50, 30 is somewhere here. So the point, the site will be these regions. So the same thing as well. All right, you may draw the tie line touching to these regions. All right. So the C node is same as well. The only difference is your temperatures here. Okay, so now, all right, if you look at this, right, if you look at this, you can, when you do the calculation, once you identify somewhere here 25, this one's intersection is about 37 plus minus or 36.5 plus minus. Then when you do the calculations, you will see the weight fractions for the solid now is increases to maybe around 50% of it. So now it's actually moving down. So you get more solid. The liquid now is decreasing. So you can speculate directly based on these regions. The larger the regions, then you know lah, the amount of solid fraction is increases at the same time. Okay. Um, that one is, I think we stopped at this point last time. So now we are moving on to the, sorry, we stopped at this point, I think, if I'm checking. So basically, this is microstructure development, how it actually forms as. So this one is a complete solubility system. Then the microstructure will be straightforward. If you remember these solidification diagrams, then you can pinpoint straight away. At point A, this is a melting point, so you may expect the structure is 100% of liquid. Right now, when you move down, when the temperature is now decreasing, right, we are talking about solidification, which is from high temperature to lower temperatures. At point B, the nucleations begins. Right, B solidification begin, and this is the nucleations start to form. So that's why at point B you can see a nuclei here, right? So this one is homogeneous nucleation, straightforward. Because consists, no, this one it could be heterogeneous, could be homogeneous, but this one is for solid solution systems. But if you move down a bit, the temperature is a bit, say it's about 1250. So at this point, point C approximately, so you can see the solid regions now start to increase. The nucleus start to grow into a bigger size, right? So at point C, at point D, towards the end of the solidifications, you can expect the majority of the phase in the form of solids. Right, we can see the changes in terms of color. Blue represent the solids. So at the end of the day, after it passed through the solidification regions, so you may expect 100% of the solid may forms, which is consists of alpha only. This one is easy. Okay,
But still, things are when you do the closing.
right. So so basically this one, so the microstructure developments for complete solution system is straightforward. It's easy because you only will end up with single phase. Okay, single phase Sahajin. But then there will be a difference, different in term of structure changes when we talks about partial or limited solubility system where you may end up with alpha and also beta. Yeah, so this is what happens. The one that you see here is a slow cooling process, right? But if you go with a rapid cooling process, you may end up with a core structure. So rapid cooling process means that up to this point, you just directly put inside the water, right? The one is a rapid cooling process. You're going to get a core type structure. All right. So these are the typical diagrams that you may see in the test 2 as well in the final exam. All right. So this diagram, they consist of, they basically partial or limited solubility systems. They lies on the solubility limits, these regions now. All right. If you look into the alpha region and beta regions, they are small compared to the previous diagrams. This one, alpha region is big. So only single phase only. But for partial and limited, you have a limited solid solutions. The remaining is the small regions, small portions is for complete systems. The remaining system, which are major systems, fall under limited partial solubility systems. These are binary system, as mentioned. Just a quick recall. Binary refer to two components. Eutectic, basically, you have special compositions here, where it is directly converts from liquid into two solids. The rest of the systems, for example, like if you go to these regions, assuming at this point, 20%, we're talking about 20% of the argentum. This one is copper argentum or copper silver systems. Talking about 20% of the argentums, 80% of the copper, by the way. So you can expect the transformations here, liquid transform into liquid plus alpha. And the last stage, we get alpha plus beta. But then for the eutectic system, which is somewhere 70% or 72% of the silver. Okay, the remaining is about 28% of the copper. You will get a direct transformations from liquid to alpha plus beta. So it skip this liquid plus solid transformations. Okay, and this process is known as eutectic. So in real applications, when we talk about melting industry, smelting aluminum, smelting and steel and so on, especially for non-ferrous material. Non-ferrous means that without iron. So copper and Ag, which is without iron. So we call it as a non-ferrous systems. Steel is a ferrous system because you have Fe. For non-ferrous systems, most of the time, you will get this eutectic temperature is very important because you will get that one is the minimum temperature. All right, the minimum temperature that you can convert everything into the liquid. Right, so that's why this one 71.9% or 72%. This case will be important compositions so that you can have a low temperature. Just hit 800 degrees C or 779 degrees C, this line. Then you can have copper argentum in the liquid state. For other compositions, for example, like in case you have this 20%, it require you to hit for these regions more than 1000 degrees C to convert everything to the liquid. So basically in the industry, the higher temperature means that you need to supply more current. So more current, technically more expenses, more money that you need to pay the current. So that's the idea. So that's why they always lies on the eutectic region. So you use less temperature, less money that you need to pay for the electricity. So those are the things. That's why this eutectic temperature is crucial. Okay. So next is that if you look into this phase diagram, you can see these are the solubility limits, the amount of argentum that can dissolve in copper. Right. So if you look into this line as well, and these are the maximum amount of the argentum, which is about 7% or 8% of the argentum or silver, can dissolve inside the copper to produce a single phase only. Okay, so if you remember how to read this diagram, from left to right is 100% of the argentum. At the same time, from right to left is 100% of the copper. So basically, you have about uh, 8% of the copper, 8% of the argentum dissolve inside 92% of the copper to form a single phase. So that one is a solubility line for alpha. And for beta as well. So beta, then you know lah, this one is a silver rich, alpha is a copper rich. So this one as well, you can expect the remaining, which is about 8.8%, right? This one is 8.8% of the copper can dissolve in argentum or in a silver to produce a single phase of the beta. This one is a solubility line for the copper to dissolve inside the argentum. This one, what does it mean by the solubility limits? So above this line, with respect to this temperature, then you can see that it start to form a secondary phase, alpha and also beta. Okay. All right. So given to you, let's say I'm giving you 40% of the sternum. So this diagram is actually sternum and also plumbum phase diagram. If you look, the diagram more or less like look the same. The patterns are the same, but the difference is solubility lines, temperatures, and also the composition. If you look into this binary system, PBSN, all right, 40% of the SN. If you look at this, 40% of the SN, it is about here. It's given to you, the temperature is about 150 as well. So you draw the 40%, and you know the temperature is 150, you get this point. But then for this point, you know the phase at present is consists of alpha plus beta, right? This point. And then for you to identify the compositions, you need to draw the timelines until it reach the boundary limits of the phases with respect to these alpha plus beta phases. You draw this line at it touch, and then you draw the vertical line to the axis. So you know this one is C alpha because this one it starts to it touch the alpha region. And you know the CA, which is about 11% of the SN. And then for beta is that you may get about 99% of the sternum. So with respect to these compositions and temperature, the compositions of phases at present here, alpha plus beta, it is about this one. All right, C alpha about 11% of the sternum, C beta is about 99% of the sternum. Now, with the same compositions and temperatures found, you can identify, you can calculate the fractions. How many percent, weight percent of the alpha, how many percent of the weight beta? Right, using the level rule. So you label those region R and S or A and B is up to you. For you to identify the weight percent of the alpha here, you need to calculate this box. Remember the concept of theta and total. Right, so you wanted to know the weight of this, you need to move these positions. You're not moving to this position, for example. Sorry. Okay, this one. So basically, once you identify the alpha here, which is S divided by R plus S, the calculation is forwards. S is CB minus C naught. For R plus S is at CB minus C alpha. So you get the numbers about weight fraction for alpha is about 67%. Because the total mixtures of alpha and beta is about 100%, you just minus straight away. 100 minus 67, you get the remaining fraction for beta, which is about 33%. Okay. So from this one as well, right, another perspective in the phase diagram. So example, I'm giving you a second system, second condition, same phase diagram, but then I change the temperatures to 220. Just now it's 150, but then I change it to 120. So you draw the same thing as well. You draw the timeline, you get the composition for C alpha and C beta. Your timeline must not exceed the phase region. Right. So once you identify this, you know this region it consists liquid plus alpha only. So once the moment that the timeline is exceeded, right? Let's say your timeline you accidentally exceeded to these regions. So now you will get 100% of the liquid. So it is wrong. So your timeline must be contained inside the must be drawn inside the respective phases only. Okay? All right. So once you identify this, you draw the timeline, then you get the numbers, you label those regions, you can calculate the percentage of the what we call liquid and also alpha. The same process using timeline as well. Okay. So for binary system, assuming let's say if you look into this diagram, the compositions, I'm giving you the compositions of the sternum less than 2%. So less than 2% would be very small here. So you draw the microstructure, so you know this is would be the liquid regions, right? Next, somewhere at this point, the nucleations start to form. Then this point, you get combinations of liquid plus alpha. Moving down, you will get 100% of the alpha. So this one is inside the complete solution systems. In case you are required to draw the what we call solidification curve, right? Sometimes the question asks require you to draw the solidification line. At this point, you get 100% of the liquids. Now at this point, which is solidifications begin, you can pinpoint the temperature, so you can estimate the temperature somewhere at this point. And this region is a liquid region, so you can speculate which is 350 sort of. So you get a liquid here, right? So next is that because this one is a complete solid solution system, you may end up with a single phase only. Single phase is easier. So you can either draw like this, or it should be more or less like small, very small steps only. That's the option this. So you get liquid plus alpha, and then moving down, you get 100% of the alpha. So these are the temperature regions, small only. Assuming this is 310, at this point would be 305. Less than that, no, it's not 310. Roughly 330. So this one is about 320. So macam tu lah lebih kurang. So 10 degree difference. So less this temperature, you will get 100% of the what we call solid. So this is in case you were required to draw the solidification curve. So but then let's say I'm giving you a different situation as well. For example, like copper is copper compositions. Let's see, not which is less than 18 but more than 2%. Just take any point of it. So for example, this point, right at this point, so you get a liquid, you get a combinations of liquid plus alpha, then you get a single phase of the liquid, a single phase of the solid. Moving down to room temperature, you get a combinations of both alpha plus beta. So in case for the solidification curve, you get this one is a liquid. This one, because this one is combination binary system, you get a significant skip features. At this point, you get this structure. Moving down a bit, right? Moving down a bit because this is the solidification regions. Okay, tak nampak lah. Saya kecilkan sikit lah. Ini, sorry. Ini, right? So the microstructure represents here. This one represent here. Towards the end of the solidifications, right? Which is this point. You get this. And if you look at this, the temperature difference as well is small. Somewhere at this point, right? Somewhere at this temperature, you will get this kind of microstructure. The combinations of alpha plus beta. Okay. All right. So if you look into this, I draw the red lines here. The red lines here basically to indicate the eutectic regions. Okay. So if you look into these diagrams again, the eutectic regions fall under this box. Okay. So why this region is important is that if you look into the macrostructure developments, if you look into the macrostructure development, you can see a lamellar structure, unique feature for the eutectic. Yeah, so you just need to remember these boxes. Next is that, let's look into the eutectic regions. So eutectic region is a direct transformations from liquid to solid. Right, you get the direct transformation from liquid to solid. Instead, you don't have the solidification for this case. If you are request to draw the solidification curve, means that it's just a straight lines like this. This temperature for eutectic. So this is liquid, this is solid. Right? They don't have the solidifications. It's a direct transformation from liquid to solid. And for eutectic compositions, you may end up with a lamellar structures. Lamellar structure, you can see the alternate, alpha plus beta is alternate. The formations is here, or diffusions here, it takes place at the equilibrium conditions. Although the composition is not 50-50, but then because of the nature of element itself, some of they grow. For example, like this one, the diffusions process occur simultaneously at the same time. So that's why you get both alpha plus beta. Okay, dia nampak macam ni. But then if you look into the previous diagram, alpha plus beta, dia macam ni. It zooms in a bit. Dia nampak macam ni. Tapi untuk eutectic, you're going to get a lamellar structure like this. And this lamellar structure, technically you will see it inside the eutectic regions. Okay, so if you look at this, these are the eutectic regions. So whatever microstructure that end up inside the eutectic regions, you're going to see a lamellar structures. Okay, you punya see compositions is this point. Dekat ini, these lines, whatever microstructure that form in this line, in these lines, this line, so whatever it is, until room temperature, you're going to get this one. Okay. But if you are required to draw the microstructure this point, all right, say the compositions of 40%, you're going to get lamella, but somehow you will have alpha rich regions. Okay, because this one is moving to alpha conditions. Okay, above this line, above the eutectic compositions, then you get a lamella with a combination beta as a rich region, for example, like 18. So how the microstructure looks like? It is like this, right? For example, I give you 40%. You get liquid, moving down temperatures a bit. You get a nucleation site, nucleations begins. Then toward the end of the nucleations, you get majority of phase is alpha. But at this region, right, these regions, you get alpha rich region. Blue color is alpha rich. You still get B, you still get the lamellar features, right? Because this one is fall under lamellar regions, rectangular regions. Okay, so this is the only one that you get a complete lamellar systems. Other than this line, you will either get alpha rich region, so which is this, or you will get the beta rich regions. Okay, right. So same as well. Assuming the microstructure is 80%, so the material that start to form first beta, because you have a beta for these regions. The beta is actually growing, and toward the end of the day, you get a beta rich region, which is red color. Before this is, if you look before this is blue, so indicates that alpha rich regions, and this one is beta rich region. So you still have a lamellar features because this one is fall under lamellar eutectic conditions. And this behavior, if any compositions, this is eutectic composition, any composition less than eutectic compositions, is that less than 61.9%, you will get hypoeutectic microstructure. So this is how it looks like. And now the terms, now we have another term, yeah, hypoeutectic. If the compositions is higher than what we call higher than eutectic compositions, higher than 61.6%, you get the hypereutectic. Okay, so now we are moving on to the new terms. Right, so you guys need to know lah the new terms. So I'm deleting this. Okay, less than this composition is known to be less than eutectic composition is known to be hypoeutectic, as long as it is inside the box. Larger than that, it is called as hypereutectic, which is you get the beta rich regions. Okay, so you guys need to know ni, jangan confuse.
Eutectic basically is to mention the state changes from one liquid become two solid. So it doesn't matter whether your system in ferrous system or non-ferrous system, you will see these transformations. Okay? Jangan confuse dulu. Ingat ni dalam non-ferrous je. Tak. Dia ada dalam any system. Right? If the system consists of direct transformation, liquid to two solid, then you will have eutectic. Okay, another system that I wanted to highlight is that the intermetallic. Intermetallic is different. Like intermetallic is like the eutectic, but then it's not necessarily eutectic because eutectic is transformations, liquid to solid, but intermetallic is a precise or it is exact compositions. Right, for example, like this red line. Only this line you can produce intermetallic. The rest of the line you get combinations of many gases. Most of the time, intermetallics are brittle. They are hard. In electronic industry, then intermetallic something that you need to control with. Because if you go through if you go through, for example, like solder ball joint, example like solder ball joint. Let me get you the actual combinations, actual structures. Okay, for example, like in electronic industry, right, you are working with chip. So this is your solder joint, solder joint combinations of SN and PB, the phase diagram that we looked previously. PBSN for this case. These are the materials sort of, but nowadays we are working with lead-free solder. Lead, lead or plumbum is a toxic material, so that's why we work with lead-free solder. So this one, if you look at this, these are the solder joint. The IMNC technically forms between the solder joint and also your chips. Okay, maybe your board. This is your chip, this is the board. So you wanted to attach the processors on the board, or the chip on the board. So you must attach using the solder joints. Okay, you cannot use a glue. This one you have attached. But then IMC layer for this case, or intermetallic compound, which is illustrated in the blue regions here, must be minimal as much as possible. Because of what? Because they are hard and also brittle. So if you have a larger line or larger thicker line of the MNC for this case, any vibrations, any impact, it just break the joints. So electrical conductivity, transfer, efficiency technically will be affected on this. That's why in most electronic industry, defect-free system is desirable. So you need to control until up to the miniature level or atomic level to make sure they are defect-free. Okay. So this one is a isothermal reaction. The isothermal reactions that we have discussed now is actually eutectic. You have another three isothermal reactions that you need to know. Okay, this one is isothermal reaction name, that is eutectic. This one is isothermal transformation or equation. It changes liquid become two solid. I label as a solid 1 and solid 2. For example, this point. Okay? For example, at this point. It changes from liquid to two solid. Alpha and beta is a directly solid lah. It's not necessarily alpha and beta. It could be another thing as well. Gamma or eta and so on. That's why I label as a solid 1, solid 2. But in the exam, you cannot label S1, SS2. You need to look into the phase diagram. What phase or form? If the phase consists of alpha and beta, then you need to write liquid transform into alpha and beta. So these are the what we call transformation temperatures, right? So you need to know the transformation temperature. Another information that you need to know is that transformations compositions or eutectic compositions, bottom of it. Okay, so normally the question asks you identify your isothermal reactions. Identify the composition, temperature, and isothermal reaction in this respective phase diagram. If you identify the eutectic, then this will be the transformations, liquid into alpha plus beta, and this will be the temperatures, and this one will be composition as well. Another isothermal reactions that you need to know is that which is similar to eutectic is known as eutectoid. The difference is that between peak is liquid, toid basically is a solid. Right? Transformation from single solid become two solid. Right? Solid 1 become solid 2 plus solid 3. So for this case is that transformation with respect to this phase diagram for eutectoid is that you have alpha transform into beta plus gamma or lambda. Right? So this one for eutectoid. So peritectic, well, basically it's a combination of both. Right? You have liquid and solid transform into a single solid. So if you look at this one eutectic and eutectoid is the shape is V shape. If you look at this, it's like a V shapes. Right? For example. But for peritectic and peritectoid, it's inverted V. Right? So we can expect lah changes. Above is one liquid, one component become two components. But for inverted V, it's two component become one component. Peritectic is combinations of liquid and solid convert into a single solid. For this case, is liquid plus alpha convert into one beta only. Another is that peritectoid is the difference is actually toid represent the solid. You have a solid, two solids here. Beta and alpha in the solid form, it converts into gamma or lambda sort of. Okay. So you need to remember this system. You need to remember the system. So let's have a look into this revision. I posted in the e-learning as well. So you can start doing it slowly. We don't need to wait for the revisions. Okay. All right. This is example of the final exam question. For question number 3 or question number 4, it carries about 25 or 18 minimum, 18 minimum marks. Yeah. 18 over 25. So in test 2, normally it carries one big question. Penting lah topik 6 ni. Because it's a combination of topic C and also topic 3. So for this question, just a quick recap. So figure 1 shows the phase diagram A and B. So a label here, moving left to the right is 100% of B. So from right to left, 100% of A. So based on these phase diagrams, what is the melting point for pure metal A and also pure metal B? So you know this one is 100% of B, means that it's a pure B. So you know these lines, right, will be 100% melting point. We're talking about melting point above this line. So what you can do, you can draw the line. Make sure you're using ruler. Jangan pakai jari sebagainya. So you draw the line, then you can get this is for pure metal B, and this one is 100% for A. Then you can get approximately somewhere here. Okay, get the melting point for these temperatures. Melting point is 100% liquid. It's the solid transformed into liquid 100%. What does it mean by alpha and beta? So they're asking you on this and this. This one is a complete solution systems. Right, the amount of B can dissolve in A for alpha, whereas for gamma for this case, it is 100%, it is maximum compositions of B dissolve inside the A.
then you can get a gamma. So this is what we call a solubility lines. Label phases, yeah, label phases A to F. Sometimes the question asks you to do a labeling. So basically, what is A? So for you to identify A, you need to look into what phases that form on the right and also the left side, not on top and bottom. You look left and right. So A you cannot identify because you need E. So let's have a look into B. B, you know, left side is a liquid. Then left side is alpha, right side is a liquid. So you know, B is a combination of alpha plus liquids. Let's have a look into C. C, you know, left side is liquid, right side is a gamma. Then you know C is liquid plus gamma. Then how about D? All right, D. Well, basically you have this point D. It's not necessary for you to look here. You can look on top as well. Example, I take this one. You know left side is alpha, but E is actually missing. But for this point, you know you will get liquid plus beta. So this one, right, we can assume it could be combinations of alpha plus beta. Okay, so because of combinations of what we call no uh oh yeah, okay, this one, sorry, this one is wrong. Okay, so D, okay, this one you know liquid plus beta. This one we know alpha plus liquid. This is a liquid plus beta. So for E, well, we yet to identify for this one. D is still missing. E is still missing. So we can speculate for this one is a combinations liquid plus, no, we don't have a liquid here anymore. This one could be beta plus alpha. And D, because you have alpha here, could be a combination alpha plus beta as well. So basically for D and E could be the same thing as well. Okay. But we cannot stop it here, right? Because if you look into E, you have a gamma here. You know this side is a gamma. You have beta here. So basically this one might be alpha plus beta. And for E is actually combinations of beta plus gamma as well. Okay, tapi for this case, it's wrong lah. This one, you know, this one is beta plus gamma straight away. This one, you cannot have beta plus gamma. Normally, it's actually beta plus alpha. This one alpha plus beta. This one alpha plus beta. Okay. Uh, right. The only thing is that the difference, the percentage, alpha plus beta, it could be more or less like alpha prime plus beta. Another is alpha prime 2 plus beta. So, tapi kalau kita buat prime pun is okay. This one is accepted one. So next question is that you are required to write two isothermal reactions. Remember V, inverted V for this case, right? So you have a couple of V here. So for example, like this one inverted V, this one is V. So the rest of it is actually side by side V is not counted lah. So you get a eutectic. One is eutectic. This is V. This is inverted V. So you have a eutectic here. Two isothermal reaction. You have eutectic conversions of liquid become beta plus gamma. Right. The other one is actually inverted V. This one liquid plus alpha. You have liquid here means that it is peritactic. Right. So peritactic convert into this one is V. This one is V, then you know lah. It's going to produce a single solid. Right? Single solid. Then we get the information. This is 100% beta. E is beta.
then this one is D basically is your alpha plus beta. E is your beta, then A is your beta plus gamma. So this one is correct based on the isothermal reactions that we have here. Right? So we have done with this. Because the question asks you name and write two isothermal reactions. You need to name first eutectic and peritectic, you get 2 mark, and this will be the reactions. You cannot follow this reaction, they want to be generic, so you need to write liquid plus alpha, convert into beta. That one is for peritectic examples. Okay, and last but not least, if you look into the revision questions, which is this one. Right now, I'm giving you the compositions. If you look into question B, just ignore this one. 50% of A, 50% of B. So you get 50% of A somewhere here. Right? The composition is easy, 50-50. So you can put it here. Yeah, unless it give you 60% of B and 40% of A. So you need to find. If you look at this, 50% of A and 50% of B, but the diagram shows that B only. So you need to read carefully. Right? This one is easy because 50-50. Sometimes it gives you 70% of A, 30% of B. So you are not reading the question carefully. You just simply label 70% here, which is wrong. Right? 70% here refer to B. Okay. Next is that once you know the composition, sketch and label the cooling curve. Means that starting from this point, assuming to be eutectic compositions. 50%. Okay. So if you look into this, then you need to draw one diagram for here, one diagram for here, one diagram for here, and also last one at least here. So minimum of 4 diagrams. Sketch and label the cooling curve. So you know this one is a mixture. Roughly, it will be more or less like this. Alright, you ada tip kat sini. So this one you get a liquid. This one you get a liquid plus beta. This one you get you need to show the nuclear grow here somewhere in the middle of it. At the end of the compositions, you get combinations of both. E is what? E is your beta plus gamma. So you need to show this. This is be 3 marks. So what faces at 500 degrees C? The same composition. Composition is fake. 500 degrees C is here. So you get liquid plus beta. So give their compositions and calculate their mass proportions. So how to get the compositions? You need to draw the timeline and touch these conditions, boundary regions. So label it as R and also S, for example. Once you know this, you draw the moving down to the x-axis, then you can get lah. Which is liquid, it is about 32% or 33%. And for, sorry, this one is for beta. And for liquid, it is about 55% estimatedly. That one is for compositions. And calculate, then you need to use a level rule. Right, S divided by R over RS for you to get the liquid. For you to get the beta, R over S plus R. For you to get the beta, S over R plus S. For you to get the liquid, R plus over R plus S. Okay, then you're done with this. Video of sketches describe the solidification process. All right. When it is solid, okay. The first question asks you about the curve. The last question is for you to draw the macrostructure changes. Okay, so that's why, as I mentioned to you, topic 6 is a combination of solidification topic as well as the phase diagrams. Okay, I have included this in your revision. Try to read slowly. It will be benefit for you for your test 2 as well as the final exam. So before we end the session, though we end for today's session, don't forget to scan the attendance again. All right. Those who scan, you may leave the room. Those who are yet, you need to scan for the attendance first. Less it won't be counted for the attendance. Right. So I'm sharing you the QR codes. Do a scan, you can leave the rooms. Those are yet to scan, then you need to wait for a while, get the QR code, then you can scan it anyway. The scan, the session technically will be available by until 5 or 4 p.m. But then the timestamp can be captured lah, at what time you scan the attendance. Okay, so with that, thank you everyone. We adjourn our class with Suspect Kaparo and Suspect. Those yet to scan, you need to wait for a while. Okay, this one. Share the screens. This one. All right.
Sir,
Yeah.
test one is up until this. There's diagrams.
No, test diagram until revision 6, revision 5 only. So
Okay.
whatever, if you have done with the revision 5, then